Section: Introduction. In this section, we explore the challenges of navigating millions of publicly available neural networks and propose the creation of an atlas to represent these models. This atlas would help us understand how models evolve, the tasks they tackle, and their performance levels. By using this structured representation, we can easily find and reuse existing models, which saves resources and reduces environmental impact. It also provides a comprehensive view of the machine learning landscape, allowing us to compare different techniques and identify emerging trends. We begin by charting the documented regions of Hugging Face, revealing the intricate structures of the machine learning model landscape. Our visualizations help us analyze recent trends in computer vision models and compare them across various modalities. For instance, we highlight differences in training practices between Stable Diffusion and Llama models, noting that Llama models exhibit more diverse training dynamics. We also show that the atlas structure can predict model tasks and their accuracy. For example, we enhance the prediction of the truthfulness QA metric for models derived from Mistral 7B by examining their nearest neighbors in the atlas. However, we find that model documentation often provides only a partial view of the atlas, as many models lack critical details about their tasks and performance. Our analysis reveals that around 60% of the 1.5 million models on Hugging Face lack adequate documentation. To address these gaps, we develop a method for charting the atlas of real-world model repositories. We identify common patterns that current approaches overlook, particularly the negative impact of duplicate models. We also recognize that the rise of model merging challenges the traditional tree structure assumption, leading us to represent the atlas as a directed acyclic graph, DAG. Our algorithm, guided by these insights, effectively recovers the atlas structure of Hugging Face, showing significant improvements over existing methods. Our main contributions include demonstrating that large-scale model repository atlases are more interconnected than previously thought, showcasing practical applications of the atlas for trend analysis and attribute prediction, and introducing a robust method for atlas charting that leverages real-world structural patterns. We also discuss related work in weight space learning, which studies models based on their weights, and the emerging field of analyzing model repositories. We build on previous efforts to recover model heritage structures, extending these ideas to real-world repositories and rethinking the assumptions made in earlier methods. Finally, we analyze Hugging Face's model atlas, which consists of a set of models, each with weights and various attributes. We describe how child models are formed through transformations of parent models and clarify that our atlas structure is a directed acyclic graph, allowing for multiple parent models in cases of merging. We highlight the vast size of Hugging Face, with over 1.5 million models and significant storage, while noting the inadequacy of model documentation. Using the available data, we construct the initial atlas and demonstrate its potential for analyzing trends, measuring model impact, and predicting model attributes, making this atlas accessible through an interactive demo website. Section Summary. In this section, we propose a method to create an atlas of neural networks, specifically charting the Hugging Face model repository, to facilitate the discovery and reuse of models while highlighting trends and performance metrics. We reveal that many models lack proper documentation, which complicates the understanding of their relationships, and we introduce a directed acyclic graph, DAG, structure to better represent these connections and improve model analysis. Section: The atlas reveals trends in machine learning. In this section, we explore trends in machine learning using the HF Atlas. Our atlas includes over 63,000 models across 28 categories, with more than 65,000 connections. We utilize this visualization to analyze trends in computer vision, CV, and natural language processing, NLP, models. When we look at the depth of models, we see that NLP models vary greatly in their depth, while most CV models connect directly to the foundational model. This indicates that the CV community focuses more on developing new foundational models, whereas the NLP community tends to refine existing models. For instance, the large language model category shows significant depth and complexity, making up nearly a third of the models, while the flux model, although substantial, has a simpler structure. Regarding quantization, we find that the vision community has not widely adopted this technique, with less than 0.15% of models using it. This suggests that vision models haven't yet reached a scale where quantization is necessary. However, we notice a shift with the flux model, which is one of the few vision models utilizing quantization, indicating that image generation models may be reaching a point where quantization becomes beneficial. We also observe a notable difference between generative and discriminative models in their use of fine-tuning methods. Most generative models employ adapters, like LoRa, while nearly all discriminative models rely on full fine-tuning. Our atlas allows us to track the increasing prevalence of adapters over time, with newer generative models showing a higher use of parameter-efficient adapters compared to older models. In terms of model merging, we find that the rate of merging in NLP is about 35 times higher than in vision models. Merged NLP models tend to have a 30% higher influence based on total downloads compared to their non-merged counterparts, suggesting that further research into merging vision models could be beneficial. We also address the challenge of charting the atlas structure, as over 60% of it remains unknown due to a lack of parent model information from uploaders. Our approach aims to recover these missing connections. We start by measuring the distances between models, using their weights as representations. The main challenge is to accurately chart the atlas structure from this distance data. To tackle this, we propose a set of charting rules based on common patterns in model repositories, such as duplication and quantization. We first cluster models into subsets that correspond to connected components of the atlas. Our strategy involves assigning source nodes and connecting unassigned nodes based on their distances to assigned nodes. We also identify and handle duplicates and near duplicates, which can confuse our distance-based algorithms. By designating exact duplicates as leaves, we improve accuracy. Additionally, we recognize that quantized models often behave like near duplicates, and we treat them similarly in our charting process. To infer the fine structure of the atlas, we utilize timestamps from model uploads, which help us determine the direction of edges. We find that most parent models have earlier timestamps than their children, providing a strong temporal constraint for our charting. We also address the complexities introduced by hyperparameter sweeps and checkpoint trajectories, which can mislead distance-based methods. By analyzing the temporal evolution of model weights, we can distinguish between these patterns and connect nodes accordingly. Finally, we adapt our algorithm to handle merged models, which have multiple parents and cannot be represented as trees. Our greedy charting algorithm processes nodes in temporal order, predicting parents and adding edges to the graph. We optimize the distance matrix calculation by subsampling model weights, significantly speeding up the process while maintaining accuracy. In summary, our approach provides a comprehensive method for charting the atlas structure, allowing us to recover the relationships between models effectively. Section Summary. In this section, we present an atlas of over 63,000 machine learning models, highlighting trends in computer vision, CV, and natural language processing, NLP, such as the preference for foundation models in CV and iterative refinement in NLP. We also introduce a novel approach for charting the atlas structure, addressing challenges like duplicates and temporal dynamics, to accurately recover the directed acyclic graph, DAG, relationships among models. Section: Charting Results. In this section, we created an atlas charting dataset based on the ground truth model relations found in the HubStats dataset. This dataset includes three connected components: Quen 2.5 to 0.5b, Quen, Llama -3.2-1b, Llama, and Stable Diffusion 2, SD. Additionally, we developed another dataset for predicting 6 attributes: accuracy, pipeline tag, library name, model type, license, and relation type. We gathered the ground truth by combining model metadata and running a language model on the model cards. We will provide more details about the dataset creation process in the appendix and plan to release the datasets publicly. For our comparisons, we evaluated a classical method that does not rely on weights and a newer weight-dependent method called Mother. Mother predicts edge direction using weight kurtosis and assumes the structure is a tree. We found that other weight-based methods could not be scaled for our dataset. We also included structure-only baselines like random edge assignment, majority vote, and Price's model, which is a preferential attachment algorithm used in citation networks. All baselines, except for random, assume a tree structure. To accommodate the majority and Price's models, we used a graph stem with known edges, containing 10% of the nodes in the connected component, and assessed all methods based on their accuracy on the remaining 90% of models. When we charted the 3 Atlas connected components, we observed that the baselines performed better than random but still had poor results. The majority approach modeled the graph as depth 1 around the root, yielding low but non-trivial results due to its simplicity. Price's model was more effective in creating a realistic structure but struggled with incorrect node connections. Mother showed better performance on some directed acyclic graphs, DAGs, but its directional predictions were weaker and lacked our additional priors, leading to lower overall performance. We visualized the predictions and errors of our methods in the appendix. Our ablation studies demonstrated that all components of our method are valuable. The greedy method outperformed the exact spanning tree algorithm by effectively handling non-tree DAGs, which include model merges, and consistently finding valid solutions. For instance, Edmonds' algorithm failed to produce a result on the SD split due to the absence of a valid tree. Our quantization prior significantly impacted DAGs with many near-duplicate quantizations, such as llama, improving accuracy by 44%. The fans and snakes prior enhanced all DAGs, particularly in hub-like structures like stable diffusion, with a 13% improvement. We also explored approximating the full weight distance with a subset of neurons, finding that using 100 neurons resulted in minimal accuracy loss while being significantly more efficient. Regarding limitations, our atlas can manage DAG structures, including merged models, but we cannot identify merges or predict parent models without specific documentation. This is an area for future research. Additionally, our atlas does not currently capture distillation relationships between models, which could be beneficial. Preliminary investigations suggest that analyzing differences between parent and child models may reveal insights about training datasets and model properties. We plan to explore this further in future work. Beyond visualizing model relations, we can also use the atlas to visualize other attributes and dynamics of model repositories. An important application of the complete model atlas is intellectual property tracking, as a model's license or data rights can affect its descendants. Completing the atlas can enhance IP integrity and prevent unauthorized use. While our work focuses on Hugging Face due to its popularity and diversity, it is applicable to other model repositories, including those used by organizations or individual researchers.